How's everyone doing? Almost the end of the week. Morning. Yeah, 12% of the class. Right. It is 8:40. We can wait a minute or two to see if more people show up. Then we can get started. I guess now's a good time to ask before we jump into material. Does anyone have questions from last time? I know we kind of went through a lot. All right. Looks like we've got uh some common issues that realloc A runs into. Not sure what realloc A. Oh, realloc. Um, I I think the one big thing that you need to watch out for realloc is it won't update any pointers that you have into the buffer. So um yeah, if you've got a bunch of stuff like directly pointing into like different offsets into that, those will all be invalidated. Um I think based on the issues that we had last time, there might be some like alignment constraints, but um I think in general, it's the fact that the pointer might change, and so any other like pointers might be invalid. Okay, let's get started. So I'm going to start by sharing my screen again. Okay, is my VS Code visible?
Yes.
Perfect, thank you. All right, so last time we implemented a linked list, or actually, let me zoom in again. All right, that is hopefully readable to people. Um, okay, awesome. So yeah, last time we implemented a linked list, we used that to implement a stack uh, using a linked list, and then we also implemented a stack based on an array. I looked over this code last night and I noticed that there was something wrong with it. So I figured maybe we could start by making it segfault, and then maybe you all can help me debug. That sound good? Oh, there's a zoom thing again. That's really cool. Okay, so the problem is actually directly with just linked list, right? So if I um, create an empty linked list, right? Maybe we can take a look at what how this function is defined, right? It allocates a struct, it sets the head and the tail to null, and then it returns the struct, which seems to make sense. And then insert tail allocates a new node, sets the value, sets its next pointer to null, sets the tail dot next to the new node that we allocated, and then sets the tail to the new node, right? This seems reasonable. Um, but down here in my main, if I start by initializing an empty linked list, and then I insert into its tail, and then I compile and I run, it segfaults. So I figured maybe we could start by like figuring out why this segfaults. Um, maybe I can uh, tell you that the problem is in insert tail, right? So the problem's in here somewhere. Does anyone want to like shout out a guess as to what the issue might be, or like what we might be able to do to fix this? Or maybe shout out suggestions for how we could start debugging? Is it null pointing to tail? Can you clarify what you mean by that? Null being the head. Ah, yes. The issue is exactly the fact that because the list is empty right now, tail is null. And so when we set tail next to new node, we're dereferencing a null pointer, and that makes it segfault, right? So what's a good way to fix this? Is empty. Okay. Um, what do I do if it's empty? Oh, interesting. Okay, let's do that. So something like this. If the list is empty, just insert at the head instead. We assume that our insert head is correct. We could set a sentinel, write a new bit of code for that. Okay. What do you mean by a sentinel? Oh, I see. Yeah, yeah, yeah. Like the dummy node and the circular doubly linked list that we were talking about in class. Yeah, we could actually do that, and that would solve all of these issues. Um, that is a good point. That is a lot of work. I mean, in the sense that uh making this doubly linked is a bit more effort, but that would probably be the correct way to do this. For now though, if we in insert tail, yeah, if in insert tail, we just insert head instead if it's empty. It looks like this works. Um, let's try calling it again, right? So this one should insert into the head. This one should now insert into the tail. Okay, it's still seg faults. I mean, obviously the problem is still an insert tail somewhere. But any thoughts on why this one's still seg faults? Not empty, but the tail is null. Exactly. Yeah. So doing this has kind of like delayed the problem, but it hasn't actually fixed anything, right? Because tail is still null. Uh, tail only gets assigned to if it wasn't null to begin with. Um, so maybe we can fix that by an insert head if head or tail is empty, then we also set the tail to our new node, right? And now that seems to work. And in fact, I can maybe print. Yeah, okay. And so now that works, right? We could alternatively, like an insert head, we're checking this condition. We could just check the dual of this and insert tail and make sure that we do the correct thing. Or we could just call insert head. That's fine. Um, but yeah, this looks a lot better now. Um, okay, so we did linked lists, we did stacks. I figured we could maybe move on to queues, unless there's questions or concerns about anything covered so far. Right. There's no questions. Let's do queues. Um, so yeah, I guess we can start with uh right. Our queue, our list-based queue, pretty much just need the same thing as stack. Uh, maybe we can copy our init function as well. Actually, maybe I just want to split screen so that I can copy and paste. Because a lot of this is just going to be the same. This. Okay, this looks good. Now I am going to need some help for enqueuing. Right, so if I take a queue and a value and I want to enqueue this, What do I need to do? How do we enqueue? Yes, enqueue inserts into the back of the list. So we have two options, right? We can think of the head of the list as the back, or we can think of the tail of the list as the back. Does anyone remember which one we usually go with for a singly linked list? Tail is the back, right? Yeah. So we insert into the tail. Actually, this will be like queue list, right? And then dually for, I guess this should return an integer, right? To dequeue, what do I need to do? At some point I have to delete, right? Delete the head. Except before I do this, I have to grab the value, right? I can maybe say, right? And then I can do that. Does delete head actually free memory for us? Yeah, it does. Okay, great. Okay. So are people happy with this enqueue and dequeue? Let's try using it. If it's empty, it won't return a value in dequeue. That's right. So if the queue is empty, then oh yeah, this will cause a null pointer dereference. So how did we deal with this in our stack pop? Oh, I guess we just assumed it worked. Um, but yeah, we can do something like assert here, right? Right. And that way, if it's empty, it fails. Or we could say something like empty, and then that, or we could return some sentinel value, or we could do something like that. Right? Let's leave that up, maybe. Okay. So maybe I'll say while not is empty queue. Uh, okay. Oh, and this needs to be okay. Okay. So assuming our implementation is correct, here we enqueue 0, 2, 4, 6, 8, 10, 12, all the way up to 18. Um, what do we expect? Uh, what do we expect is going to be printed here? If we're enqueuing a bunch of things and then dequeuing them? Let me make sure it compiles first. Great. There we go. All right, now that it compiles, what do we expect this to print? Anyone have a guess? FIFO, yes, first in, first out. So in particular, it's going to preserve the order that things are enqueued in, right? We run this, it prints things out in the order that we enqueued, right? So it goes 0 to 4, 6, 8, up to 18. Whereas if you remember for a stack, it kind of reversed the order, right? Okay, so this is kind of the easy part of queues. Let's try doing an array-based queue. All right, I am going to need help with this. So what do we start? What fields do we need for an array-based queue? Let's assume that it's holding integers, right? So we need a buffer of values. We need two pointers, yes. What do I call my pointers? All right, int front, int back. Great, and maybe I'll move these. Oop, that's not what I want. Maybe I will move these to be up here. Do I need anything else? I need the buffer size. Yep. There we go. All right. Does that look good? No. What else do I need? Front and okay, yeah. So this is we sort of talked about this, right? Front and back can be pointers, or they can just be indices into buffer, right? So I could instead of saying like dereference front, I could say buffer at front, right? Either is actually viable. It's just if I keep them as indices, then if I ever reallocate buffer, I don't have to change the indices. Or I don't have to like I can use the same indices, they'll just be offset from a different base point. Okay, so let's initialize this. Right. Int counting the number of elements we allocate. Um, so buffer size is going to be like the maximum size, or like buffer size is going to be the size of the allocated buffer, right? Do you want like an int representing the size, like the number of elements in the queue right now? Actually, any guesses on how we can compute this given a queue? Back minus front, that's right. Yeah. And then buffer size is just the size of the buffer that we've allocated, right? So yeah, you've redeemed yourself. Okay, let's initialize this, right? So what do we start front as? 0. Great. All right. And then back is also 0. Perfect. All right. Now let's set q.buffer, right? Malloc. How big of a buffer should we make? Let's do 8 again. And then we can set buff size to 8, right? Is everyone happy with that? Sweet. All right, let's move on. How do I enqueue into an array backed queue? Q.front needs a semicolon. Thank you. That would have been so embarrassing for me. Okay, yeah. So how do I enqueue into an array backed queue? Anyone remember from lecture? Right. Let's do that. Right. And then if I go to DQ, maybe do the dual of this, right? So I can return what's the index for what I return? Return the value and move front. Yeah. So uh do I pre or do I post or do I pre-increment? Post. Thank you. All right. So we've got our queue here, right? There's a couple issues with this implementation. Does anyone want to take a stab at what they are, or should we play around with it and run into an error? Shrinking the size. What do you mean by shrinking the size? Lacking the ring buffer. That's another good one. Yeah. Um, yes, exactly. Yeah. We waste the memory that we've incremented past, and the way to fix this is a ring buffer. Thank you. So how do I how do I correctly implement this with a ring buffer? First of all, do I need to change anything up here? Yeah, I can use the buff size as my end, right? So I don't need to add any fields to this because I already have the buffer size. Init is also the same. All right, so what do I change in Q? Update the backend mod end. Yeah, so if I do this, I can say mod, and then I'll use buff size. Yep, exactly. Uh, Buffer back equals value. Because we're incrementing, we're moving back to the next index, right? If you um, remember, let me annotate again. This is so fun. Here we go. Here we go. Here we go. Oh, this is fantastic. Okay. So if you remember our queue that is backed by an array, right? Any chance to use that? You're right. Okay. So we've got maybe front here, and let's say we've got like a couple things in queued already. And so here's back, right? If I'm enqueuing something else, oh sorry, back should be one past this, right? So assuming it's been set up correctly, right? If I'm enqueuing something else, I want to write maybe a 4 into here, right? But now the next place that I can enqueue is over here, right? So I need to move um, the eraser. There we go. There's the eraser. Yeah. So now I need to move back uh, over here, right? And then if the queue is all filled up, but maybe front has moved as well. Like if back makes it to the end, um, and so here's front, right? And here's back, and I insert the 7, then I can't just increment it because that would run out of bounds of the array. Yeah, it's exactly. It's just doing the post increment, but like uh, we could do something clever, right? We could say something like oh yeah, we could say something like plus plus, or like yeah, we could put the plus plus here, and then say um, this mod equals buff size. That's fine too, right? It's doing the post increment and then it just reduces it mod buff size or mod n. That's fine too. Um, actually, may as well leave that in there. Okay, so maybe this gives you some idea of what. I'm gonna clear these annotations. All right. So if this is how we fix in Q to do a to make it a ring buffer, what can we do for DQ? Same thing, right? So maybe I'll grab the value first, right? And then return the value, but in between, I'm gonna say mod equals. All right. Does this look good? Okay. And then how do we check to see if our ring buffer Q is empty? Like what's the empty condition? Back minus front mod n, right? So while Q back minus Q front mod Q buff size does not equal 0. So while it's not empty, right? And so now, even though we've allocated, oh, so actually this is going to run into an issue because we've allocated space for 8 elements and we're trying to enqueue 10. Let's try with 5 first. Are you invalid type struct Q? What are you talking about? Oh, this is not a pointer. This is why you don't code live. Q undeclared. What are you talking about? 202? Oh, let's call this Q. There we go. All right. Okay. This seems to do the right thing. In particular, if we let's do the sort of pathological thing, right? Where we um enqueue and then immediately dequeue and then uh equals. Let's just print these out. Oh, wait, we make it go up to like 20. That actually wraps around, right? And we can see that yeah, here we go. So we can see that it's doing it's enqueuing and dequeuing correctly, and then when it gets to 7, it wraps back around to 0 every time, right? So we can kind of see our ring buffer working correctly. Hopefully that's convincing. We could also inside enqueue, right? We could check to see. Actually, how do we check to see if the queue is full? How do we check to see if we need to resize? Like, what's the resize condition? I Oh, back minus front equals buffer size. Let's see. Um, so Uh, we can't check the stack pointer because this is a queue, right? We don't have a stack pointer. We have two indices that we have to work with somehow, right? Let's just print that for now. Um, and see what it looks like. Actually, is this ever going to happen? Well, let's find out, right? Let's try enqueuing. Um, yeah, let's just enqueue 20 things. Okay, doesn't look like it printed um, need to resize, right? So in particular, it doesn't look like it actually resized. So if I maybe go here and I say, right, this just DQ'd 32, 34, 36, 38, and then 24, 26, 28, 30, 32, 34. Like it's just DQing those things repeatedly, right? We expect the first thing to be DQ'd to be zero. So apparently this hasn't worked, right? I think in particular, um, it didn't resize. Well, I guess we're not actually resizing it, but it didn't recognize that it needs to resize, and so it's just like overwriting itself. Um, you don't need to resize if you use DQ, right? Um, if you Yeah, so the problem is at the end of this for loop, this queue wants to hold 20 elements, but we've only allocated space for 8 in the array, right? When it's a linked list, we can just create new nodes and we can link them onto the list, which is fine. But when we're working with an array, um, everything has to be pre-allocated. And so if we've only allocated space for 8 elements, then there's no way that we can enqueue more than 8 at a time. But we might want to, right? So like if you remember our stack, let's do push array. Yeah. So here we checked if the stack pointer is greater than or equal to the buffer size. This checks for overflow. And then if it overflows, we grow the stack, right? So I guess I'm trying to figure out what the equivalent of this is for a queue. Yeah, right, exactly. So eventually back will, if we don't grow the queue when we need to, eventually back will just loop around and start overwriting the front. And so it'll like overwrite stuff that's already there. Because it'll only ever hold 8 elements at a time. Right. So what is our resizing condition? Check if at front. What do you mean? Check if what's at front? Font size -1. Okay. Let's try that. Um, okay, let me pull this up. Okay, great. So printed need to resize a couple of times. So that seems reasonable, right? If we think about why, uh, the back pointer would be closer to the head of the array than the front is yes, yes, back would have looped all the way around, right? So when the well, I really will use any excuse to do this, won't I? Okay. So okay. So if our front is here, right? And our back is, let's say, here, right? So it's wrapped around. That means this, and this are these three squares contain values in the queue, right? If we enqueue again, now this contains a value for the queue. If we and then back moves to here. Um, but there's still an open space, right? If we enqueue one more time, then back moves to here. So back equals front, and the queue is full. The problem is like because back and front are both working mod n, if we didn't have this, back minus front is never going to equal n, right? If I have two numbers that are between 0 and n minus 1, their difference is never going to equal n, right? Their difference equaling n would be the same as their difference equaling 0. Now I could say if back equals front as my resizing condition. But the problem is now I can't tell the difference between an empty queue and a full queue, right? So I may as well, um, I guess, yeah, we can just resize when we've got one element left. Or we could do something like check both of these and then check to see that they're not at 0. Because if they're both at 0, then we know then we know it's just started. But if we never dequeue and this like wraps all the way around, then it would go back to 0. So actually, yeah, the best we can do is back minus front mod buff size equals buff size minus 1. So let's try that. Right. And then when I resize, what do I need to do? We can maybe say that. Let me see if I can get realloc to work. It's the pointer and the size. Okay, so I take Q buffer, Q buff size. Right, okay. So I can do this, right? This is effectively what I did for the stack, right? Oh, man. It's like a manual page. Especially for like POSIX functions, like a lot of basic C functions are going to be documented this way. Um, yeah, so you just type man and then the name of the function. So I can do like man printf or something, and it'll show me the documentation for printf. This is what I do instead of memorizing function arguments. Uh, but yeah, um, right. So when I was pushing to a stack array, this is basically what I did, right? I allocated a new buffer and I set the new buffer size. And I think here we were playing around with different ways of growing the size, but we might as well just double it for now. Is this, yeah, is this good? Is there anything else we need to do? We can find out. Okay. Apparently, I just am not gonna. Yeah, there will be an attendance poll. Um, Actually, yeah, for the attendance poll question, um, let's make this the attendance poll question. What else can I do when I'm resizing? Multiply the size by size of int. Yeah, thank you. Is there anything else I need to do while resizing? I guess I can say q buffer equals new buff. We can say Okay, actually, that seems to work. Um, the thing I was thinking of is uh, if your elements are kind of somewhere in the middle, then you can um, wrap them around. Like, oh, wow, cool. Zoom is cool. Um, I think so. I think what you want to do here is start at start at what is it, front, right? Something like this, and just copy everything over to the beginning uh, of the array, um, because otherwise, if I've got like two, three, four, right? If this is what my queue looks like, where this is the front and this is the back, and I resize, pretend this is 10, right? Or pretend I know how to count. If I just resize and I don't do anything else, I'm gonna get a four here, a two and a three here. But now there's gonna be like the queue expects this to wrap around here, right? And so now if I leave back and front and I try to DQ something, it's going to DQ or right, it's going to DQ the two, then it's going to DQ the three, and it's going to DQ a bunch of zeros before it gets to the four, right? So when I size up, I also need to start at the front pointer and basically move everything. Uh, like I need to reset front to zero is what I'm trying to say, right? Do people believe me on that? I guess before I clear. Yeah, or I guess actually, so with malloc, you don't have any guarantees on what the remaining elements are going to get set to, right? So like if I DQ from these empty spots, uh, I cut off. Can I repeat the last minute? Yeah. So if I start with a queue like this, right? It's got two, three, four. Um, this is as far as a ring buffer is concerned, this is fine because the two, like if I go off the two, three end, I wrap around to the four. But if I resize this, now I've got a whole bunch of like blank spaces between the two, between the three and the four. And so if I try to DQ, I'll DQ the two and then the three, then I'll get a bunch of garbage values before I can wrap around to the four. So when I resize, I need to somehow like shift all of these back into the new buffer, right? So I can reset front to zero somehow. Does that make sense? Um, since I already said that, maybe for the attendance poll, we can do something like besides a ring buffer, how else can you deal with uh, with like not wasting space in queue array? Thank you. I do need to free queue buffer. Yeah, catching that memory leak is more than routine to you. Um, all right, so we'll leave that for the attendance poll question. Um, there's a couple other things that I wanted to talk about today. I guess we have a little bit of time. Uh, yeah, okay, let's do it. So if you remember, Um, from maybe let me stop sharing this and let me pull up the linked list slides. There we go. Right. Okay. So if you remember when we were talking about linked lists, I started by talking about how good arrays are, right? Elements are packed densely. I only have to do one memory allocation. Random access is a lot easier. It's really good for the cache because as soon as I fetch one thing in memory, it like gives me the whole thing at once. Um, and then the problem with arrays is that like inserting and removing from the middle is kind of annoying, right? And so we use linked lists to fix that. Um, it turns out that you can actually build a linked list on top of an array. So the same way that we have like stacks and queues backed by both arrays and linked lists, we can make arrays that behave like linked lists. Um, and the reason I'm bringing it up now instead of during the linked list lecture is because the way to do that uses stacks. Uh, so I figured maybe I could introduce that in the last 10 minutes, uh, unless there's other questions on stuff that we've already covered. All right, let's do this. Gonna, okay, create a new whiteboard. Can people see this? Yes, okay, great. Um, I just realized I don't know how to make it so that you all can't draw on the whiteboard. Uh, please don't. Maybe I shouldn't have said anything, but yeah, I'll figure that out before next time. Okay, so um, right, okay. So when we have a linked list, all right, well, whoever that was, I guess I can't really fault you. You can't see. Like you can't see the whiteboard. You just see a white screen. Is there a let's do this. All eyes on me. There we go. Cool. All right. Glad that fixed it. Um, right. Okay. So when we have a linked list, uh, these nodes can be just about anywhere in memory, right? So I might have like another one here, and this might go from here to here or something like that. And there's like no, um, there's no sense of locality between the different nodes, right? The obvious way to fix that is I can put all of my nodes into one giant array, right? So I can start by pre-allocating an array. And I'm going to call this like a pool. Okay, turns out I don't know how to write super well with this. Is that better? Um, and then every element of the array is going to be its own linked list node, right? And I can keep a stack of free indices somehow, right? So like 0, 1, 2, 3, 4, right? And I can push all of these onto a stack. 0, 1, 2, 3, 4. Actually, maybe I want to, this is fine, whatever, right? This is the stack. And so when I need a linked list node, I pop the top index off the stack and I call this my node, right? And then if I need to connect it to something else, I pop the next index off the stack and I connect it to that. And if I need to connect that to something else, I pop the next index and I connect it to that. And now if I want to delete three, right? Normally what I would do is I would update the next pointers so that four goes directly to two, right? But now somehow I need to free this chunk of memory, except since it's all part of like a pre-allocated buffer, since it's all part of an array, I can't just like free one block at a time. But what I can do is I can push this index back onto the stack. So I can take, oop, so at this point I've popped, the stack just has 1 and 0 on it. But when I free three, I can push three back onto the stack. And so now if I need to allocate a new node, I can pop three off the stack and connect it to that, right? So alloc is just pop off the stack. And then free is just push onto stack. Can everyone see that? Also, does that make sense conceptually? Yeah, I can repeat that. Um, yeah, so the idea is I uh, instead of asking malloc for a chunk of memory, and it gives me like a chunk of memory somewhere random on the heap, I can pre-allocate a whole bunch of memory, and I can push like I can basically start by pre-allocating a whole bunch of nodes, right? So let's say I know my linked list is never going to grow bigger than 20, right? Maybe I can set like an upper bound, and I can pre-allocate like 32 nodes or something like that, right? And I can push all of these nodes, all these linked list nodes onto a stack. Or maybe I can just push like the indices of these nodes onto a stack. And then every time I need to like every time I would malloc a node, instead of mallocing a node, I can just pop one off the stack. And I can just like I basically keep like a stack of unused nodes, right? And so anytime I need a new node, I just pop one off the stack. And so I know it's unused. Yeah, and the exactly the order doesn't matter, right? And so I can link these around in some like weird order depending on how my access has worked or whatever. But every time I pop one off the stack, it's going to be unused and it's going to be pre-allocated for me, so I don't have to worry about allocating it. And then when I want to free it, I don't actually have to free it. I can just push the index back onto the stack so that the next person who wants a node can just pop it off the stack. Or like the next time I want a node, I can just pop it off the stack. And then at the end of my program, I don't have to go through like loop over all my linked lists and free them. I can just free this entire array at once. There we go. Yeah, I can just free the entire array at once. It's also worth noting, uh, as in like I haven't like this entire array was created with a single call to malloc, right? Like I asked the OS for one chunk of memory at the beginning of my program. And so at the end of my program, I can just free the array. I don't have to loop over all my linked lists and free them, like free all the nodes individually. So I don't have to worry about like accidentally missing something. This is sometimes good. Like if you can place an upper bound on the size of your linked list, this is great because you can just pre-allocate those nodes. And if you know you're going to be like inserting and removing things a lot, um, this can be useful for something like that. And then you don't have to worry about like resizing or shifting things around or whatever. Um, and yeah, so it's I guess it's worth noting that like one allocated pool can represent multiple linked lists, right? So I could have an array with a bunch of nodes, and I have one linked list that does this. I have another linked list that does this, right? And so this one pool or this one array is tracking two separate linked lists, and that's perfectly fine. It just has one stack of nodes. Ah, is it more favorable to use the additional memory for a stack than to spend time allocating and deallocating memory, given that you know the upper bound? So often it's not, right? If this like you'll see this pattern used a lot in like game programming or something where you've got like a whole bunch of objects you have to be spawning and deleting all the time, and so you'll just pre-allocate like a pool of objects so that you don't have to like waste time calling the memory allocator. But it turns out I'm actually kind of lying when I draw the stack as a separate thing, because we can also implement a stack with a linked list, right? And so we can start with this linked list or this array representing maybe let me move down to here and get some more space. So we can start with this linked list just representing all of the unused nodes as a stack, right? And then popping off the stack is like removing something from the head, right? So I just keep track of like unused points to the head of this linked list. And then when I want to use something, I just pop, I pop off the unused stack, which means unused goes to here. And now I have this node that I can do whatever with, right? And then when I want to, so let's say I've like done a bunch of stuff and um, maybe I've used maybe I've used a few nodes, right? Maybe I've done something like this. And so now unused is pointing here. And then I want to free this node. I can just push that onto the unused stack. I know there's a lot of arrows all over the place, but the point is, because all of the nodes that are on the unused stack are going to necessarily be disjoint from all of the nodes that I'm using, they can both just share the same like allocated chunk of memory. And so I don't need to use any additional memory. All that I need to know is what the upper bound is going to look like, right? And if I'm not memory bound, if I'm not running on like an embedded device or whatever, like who cares if I allocate 10 megabytes worth of nodes, right? It's 2024. We have enough RAM for that. Um, anyway, uh, maybe next time I can show some example code for this sort of thing, but it is 9:41. Again, sorry for running over. Uh, you are all free to go unless there's questions, in which case I will happily answer them. Good 5 minute coding adventure. Glad you found it fun. Yeah, the strobe lights. Have a good one. Yeah, the attendance poll. So when we have queues, like you enqueue queues backed by an array, when you enqueue and dequeue, like the front pointer keeps moving up. One way to deal with that is by using a ring buffer so that it wraps around. Uh, what's another way of dealing with that problem? We also talked about this in the queues lecture, I think, if you want to take a look at that.